So yeah, it's problem 10. But how I understand this is that you have this set of two-sided ideals, and this set does not contain any ideal which is not equal to 0, I guess.
Does that mean that it only contains the zero ideal?
No, it can contain the unit ideal. Remember the ring itself.
This is an example of an ideal that contains no element A not equal to 0.
Contain no element that is um not sure. I mean, um, you do not have the additive identity if that's what you're talking about.
Every ideal has to have the additive identity
Yeah, I
because it's
mean,
a subring.
yeah.
I wonder if it made more sense in French than they did.
I do not know French.
Not sure whether I have a copy of this book in French.
I saw the commutative algebra one in French. Yeah, this problem is interesting actually.
I guess I don't really understand the hint, so that's not very helpful.
Yeah, so,
Set of
yeah.
ideals containing no element A not equal to 0. That's a couple of negatives there. So it
Exactly.
sounds like if you cancel the negatives, then it's saying the ideals containing only the element 0. And that doesn't make any sense, because
Or
there's only one ideal that contains only 0.
yeah. But right. I mean, the thing is, we have to show that the intersection of all these irreducible ideals reduces to 0, so it's equal to 0. When do you think it will be 0? When they are... wait. If you can show that the intersection of all the irreducible ideals is irreducible... Wait, no. That can't be possible. Um,
It could be, I just don't know.
I mean,
Going back to Z,
yeah,
there's a nice infinite chain. You can take 2Z, 4Z, 8Z, 16Z.
yeah.
That forms a nice nested chain of
Mm-hmm.
ideals. Those are all irreducible, and their intersection is 0.
Mm-hmm.
Uh, but I think that in Z, 0 itself is not irreducible. So I think that you can have the infinite intersection of irreducibles be reducible.
Be reducible, right?
Because I think that 0 is irreducible in Z. I keep flipping on that. 0, I believe, is irreducible in Z. Well, it is from pure knowledge, because 0 is a unique factorization domain. Is that what you just said?
Mm-hmm.
You want to look at some of the other problems, or you want to chat about this while we wait for some more folks to show up?
I'm not sure if Henry said he will not be able to
Hey, Cheer.
join. Yeah, cheers there. Yeah, we do have our other problems. 8 is an interesting one about nilpotent ideals. Um, let's see. Cheer, do you have a specific problem you want to talk about, or else? I think we can spend more time on 10.
Which do y'all find most interesting?
Sorry?
So which problems did y'all find most interesting?
9 was the least interesting. 7 was kind of interesting. I hadn't worked with polynomials before in the context of forms.
Mm-hmm. Well, I don't know whether 4 was interesting, but probably important.
Okay, so if you're looking at the screen, there's this problem from Nat.
I'm sorry, I wasn't here. But I am...
Yeah, so he talks about reducible and irreducible ideals. So an ideal is reducible if it is the finite intersection of ideals strictly containing it. Okay.
Wait, where's that? Which problem?
Problem 9. Sorry, problem 10 here that I'm showing.
Yeah. Now, I think that in Dummett, when he talks about it like in chapter 15 after he's been working with primary ideals.
Okay.
We haven't dealt with primary yet.
Okay. I mean, even Bourbaki
And
hasn't talked
what?
about that.
This is from app.
Yeah, Nat. The second book, I guess. Yeah. So yeah, he talks about this, but let's see which section is this exercise of. But yeah, like in Damit, is there anything like similar to like using the Zorn's lemma to prove something?
The first use of Zorn's lemma was the one that we saw
Yeah.
yesterday. And I think that it mentions, like you did, that another popular time people might see Zorn's lemma first is showing that every vector space has a basis.
Mm-hmm.
That's what you mentioned that you had seen in that differential equations class.
Mm-hmm. Intersection.
Nope, that's not the one.
Inductive. I'm not sure what the inductive Something means here. The set of two-sided ideals contain no element a not equal to 0. I'm not sure, but like these ideals can contain other non-zero ideals. Um, and inductive seems to me that um, the ideals increase um, in their size. I'm not sure. Mm-hmm.
I was trying to see if I could find a copy of Bucky in French, and I cannot. I can only find the English translation.
Yeah, I think the only ones that are um, available online are like by Springer. I'm not sure if Springer publishes anything in French.
Yeah, but Springer loves selling ebooks, so I figured there must be a copy somewhere. I'm sure there is, but
Okay. So in an Etherean ring, whatever, every ideal is a finite intersection of irreducible ideals. Somehow.
I'm not positive about this, but you know how when we apply Zorn's limo, we have to show that every um, well-ordered chain contains an upper bound. I think that an Etherean ring is one where every increasing chain eventually terminates. So eventually, it's A is contained in B, contained in C, contained in C, contained in C, contained in C. So I
Hmm.
think that when you have a ring with that extra restriction, you don't have to prove upper bounds. It's
Yeah.
guaranteed by the nature of the ring.
Yeah.
Stabilizes, I think the word they use. You have ascending chain conditions and descending chain conditions, but that's about all I know. I think that means you can avoid using Zorn's lemma.
Okay. You could maybe also speak on in as to what we're working towards right now.
We have the P set, and this is the last problem of the P set that we're stuck on.
There's some folks here. We might want to just kind of skim through
Hmm.
other parts and circle back to this.
Okay. Hmm. Hmm. Okay. You know what? We'll go through the other problems and then we'll see what we're gonna do with this. Yeah. This is all in one page. Let's go here. Um. Yeah. So let's see. Hmm. Yeah, does anyone have a problem that they want to talk about so we can like focus more on that? I can't get my head out of this problem. Hmm. Hmm. Have you thought of like applying the Chinese remainder theorem in some way? Because A mod the set of all sorry, the ideal generated by the set of all reducible ideals can be isomorphic to the ring quotient from A mod and of each of the ideals. And if we can say that, wait, if we can say that, would like if the intersection of ideals is 0, what does that say about the quotient rings that the ideals produce? So if you have like I1 intersection I2 intersection I3 is 0, can you say something about A mod I1 intersection A mod I2 and A mod I3?
I thought about that a little bit. One thing I kind of searched around for online was whether there's any characterization for the quotient of a field by an irreducible ideal. And I saw some comments on Stack Exchange saying that there's no nice characterization. Like if you take a ring mod maximal ideal, you get a field. You take the quotient of a ring by a prime ideal, you get an integral domain. But we're saying here are some examples of why you can't come up with something nice for the quotient of a ring by a maximal ideal. But just skimming the examples didn't make sense. So the only takeaway for me was there's no nice property. You can just say, oh, well, since this is maximal, the quotient has this property, and now we're going to be able to do something with it.
Yeah. So here, maximal, anything that says to me is that it is not irreducible, right? It cannot. Sorry.
It depends on what set and what I'm sorry. It depends on what set of ideals we choose as
No,
the ones
I'm
that we're looking at,
no.
and
If you
what the
like,
order relation is.
yeah. I mean, if you have like a maximal ideal from the set of ideals, then it's going to be maximal ideal for the ring. If you're, of course, if your ordering is the chain. Um, hmm.
Yeah, the confusing thing here is that I mean it's going to be Thorne's limit says it's going to be maximal with respect to that
Set,
partial ordering
yeah,
that
set and the
you're
ordering.
using, not necessarily a maximal ideal in the way that we defined it.
Yeah, Atia, but like Atia did that to get the maximal ideal, right? Hmm. Mm.
Yeah. Could you talk me through what ideas you have for the problem?
The problem is this one. You can check the key set that is uploaded in the chat. Last problem.
It's this one, number 11 on this page is the last one on current P set.
Okay, so if we do work with the integers, so a is the z, and so you have the irreducible ideals. The irreducible ideals in z are going to be pz, or the prime ideals. Okay. Now if you consider the intersection of all the irreducible ideals of these kinds, so you have p1z, p2z, p3z, and so on. You have to show that this reduces to 0.
I think I might have it.
You have it?
I think I have maybe a good idea.
Okay, let's hear it.
So I think that as stated, the hint doesn't make sense.
Okay.
But let's give it a different reading.
Okay.
Let's say that pick an element A, pick a non-zero element A in the ring,
Okay.
and let's look at all of the ideals which do not contain that particular element.
Okay.
Okay?
Okay, ideals not containing that element.
Let's apply Zorn's limit to that.
Those set of
So
ideals.
our set of ideals is going to be all of the ideals that omit a specific element A.
Okay.
We're going to arrange those by containment, just like before. It's non-empty because the zero ideal does not contain A. And we're going to show that every chain has an upper bound just by unions, just like yesterday.
Okay.
So that means that contains that set of ideals that omit A has a maximal element.
And
that maximal element is actually a maximal ideal. In a sense we talked about yesterday, it's just a genuine maximal ideal. Okay. Every maximal ideal is prime. Yeah. Correct? Is it?
Wait, every prime is maximal.
Oh, so that's not.
Let me just check.
So what I want to know is whether this maximal ideal we just created is irreducible.
Every maximal ideal, if your ring is commutative, is a prime ideal.
So maximal means that it's prime?
Yeah. If your ring is commutative. And I guess we have to assume commutativity here.
And it is.
Okay.
And everything prime is irreducible.
Yep.
So what we just did is we showed that for every element A, there is an irreducible ideal that does not contain A.
Yeah.
We can do that for every non-zero A.
Okay, yeah.
For every element.
Yeah.
So now if we take the intersection of all those guys,
we're going to get
it has to omit everything except for 0.
Yep, yep. Wow. Wow. Wait.
And then I think that B is just going to be using that lattice homomorphism theorem or something.
Yeah, the last isomorphism theorem. Yeah.
Something like, yeah. I think.
This is great. Wait, let me recheck everything. So the set we're creating is the set of ideals I1 till In, and these ideals are special in the sense that each of them do not contain a specific um, element from the ring that is non-zero. Okay. Um, okay. So.
And I need to add the word proper in there too. I need proper ideals that do not contain A.
Yeah, proper ideals. Right. Yeah. Okay. So these ideals form a set, and you apply the containment to partially order them. So you have a partial ordering, which is a chain of ideals containing one another. Okay. Yeah, and then like yesterday, we can apply Zorn's lemma to get a maximal ideal which does not contain this, which is irreducible and does not contain this specific A, right? But the thing is, the proof asks you to show that all the irreducible ideals of A, when they're intersected, go to 0. Can you show that this set of ideals that we created, which like omit, would they constitute set of all ideals, all irreducible ideals?
No, but the intersection of all ideals would be contained in the intersection of this subset. So if I want to intersect all of the irreducible ideals, then first of all, I'm going to intersect some of them, ones that we've just been talking about.
Yeah.
And the intersection of those is already 0. So if I intersect with even more of them, it's still going to be 0.
Okay. Yeah, but the thing is, are all irreducible ideals of this form?
No, but each one of these is irreducible. I was saying, let's intersect all of the irreducible ideals.
Okay.
I'm going to be selfish. I want to intersect mine first.
Okay.
And by the time we get finished intersecting mine, we've already eliminated everything except for 0. So I'm going to go home now while you finish intersecting the rest of them.
Okay.
And every ideal contains 0, so you're never going to eliminate that one.
Okay.
But you also can't make that set any smaller.
Okay. I think, okay, so by inductive, you meant that like you can just like start from like canceling one element out of the ideals and then repeat canceling other elements, isn't it?
I'm not positive. I think that they might mean that an inductive set is a partially ordered set where every chain, every well-ordered subset has an upper bound. I think that's technical language for satisfying the conditions of Zorn's lemma. I think let's hop to a new window and look up inductive set. I think that that's a term of art. So it says, Wikipedia says, so it must be true. In Bourbaki, an inductive set is a partially ordered set in which every totally ordered subset has an upper bound.
Okay,
In
okay.
other words, it's a set fulfilling the assumptions of Soren's lemma.
Good lord. I thought it was something to
Of course, that comes from the set theory book.
Ah, okay. Okay. I haven't touched that. This can be controversial. Come on. I mean, the thing is, when you hear inductive or induction the first time, you just assume that it has something to do with the induction proof process. But okay, so that's helpful.
Math is so bad about that, using the same word to mean a million different things.
Especially when your math teacher is Bobaki. This is great. Okay, so yeah, good lord. Okay, that was nice. I should write this proof.
I'm blaming the translator of the book for botching the hint.
Yeah, I mean, if he had told us that it's actually about a partial ordering, I mean, it would have been much more clearer. Okay, so his theory of sets book. Okay, so this is cool. So yeah, in short, the trick was to get these ideals, like subtract each non-zero element, and then take their chains, get the maximal ideal by Zone's lemma, and the maximal ideal is not going to contain this and is going to be irreducible. So you take the intersection of all these maximal irreducible um, ideals not containing these elements, and you run out of elements, and thus you're going to be left with 0. Yeah, this was great. This discussion was really productive. And for B, you have to deduce that every two-sided ideal is the intersection of all the irreducible ideals which contain it. Okay. Um, yeah, so we have to go back to that fourth isomorphism theorem. What was that? If you have an ideal, you have a correspondence between the um, subrings that contain the ideal and
So something not obvious
yeah.
is we'll just need to see whether the pre-image of a irreducible ideal is irreducible. If so, then we can use this lattice isomorphism theorem.
The under homomorphism.
Yeah.
I guess it is. I mean, okay. So if you take the pre-image of an irreducible ideal, Hmm. Hmm. P to the NZ is also irreducible. Yeah. Every two-sided ideal.
So that theorem you were just looking at said that there's a one-to-one correspondence between ideals of A and ideals of R and ideals of R, the quotient of R by I.
Yeah. You're like.
So wouldn't that mean if an ideal was the intersection of two other ideals in R, then if we map over to the quotient, the image would be the intersection of the images?
Right. So if you have like I is equal to J intersection K, like when you map, you're going to have the intersection of the images, right?
So that does sound then that irreducible ideals map one-to-one to irreducible ideals. So irreducible ideals in R map one-to-one to irreducible ideals in R cross I almost. Not one-to-one.
Mm, right.
Or
So
maybe it is one-to-one.
if you have like an intersection, so when you map the ideal that is reducible, then what you're going to get is like um yeah, okay, so you're going to get some intersection um in the codomain that represents the image of the ideal, right? But in the case of irreducible ideals, when you map them, you cannot form an intersection that represents the ideal. Sorry, the image of the ideal. Mm-hmm.
So that's what sets up the one-to-one correspondence between ideals, sorry, between irreducible ideals in R mod I that contain 0 and irreducible ideals in R which contain I.
Hmm.
So if 0 is the intersection of all the irreducible ideals in R mod I, then I would be the intersection of all the irreducible ideals in R
Which is,
contain I.
yeah,
And I think that's basically what we're being asked to show, only they use that weird letter A for their ideals instead of I.
yeah, that Greek. No, no, it's not Greek. Something else. Mhm. Hmm. I mean, do you really need that? So if you have a two-sided ideal, um, what you try to do is like have irreducible ideals which contain it. Okay. Um. Mhm. Okay. Okay, I'm not sure. This is probably stupid, but what I'm thinking about is that you have an ideal J that contains I. Okay, and J is an irreducible ideal, and like before, what we do is you have the J minus a non-zero element from the ring. Okay, so you have this J which does not contain this non-zero element uh, contains the ideal I. And what you do is you construct such J's which contain I but do not contain such A's, non-zero A's from the ring. And these ideals which contain I, when you take the intersection, you're going to get rid of all the elements except the ones that constitute the I. I'm not sure. This is probably stupid. Do you think that can work? Um, I mean, Yeah, you have to show that there exists such J that would contain it. I mean, mhm. I mean, yeah, I mean, yeah. I'm just trying to apply the same logic, but
One thing I realize I'm being too casual about is the way that intersections behave under homomorphisms. It is
hmm,
true that the pre-image of an intersection is the intersection of the pre-images, right? But maybe not the other way around.
wait, intersection pre-images. So the pre-image of the intersection is the intersection of the pre-images.
Think so?
Wait, so P
So
inverse of
this is actually just a set theory
yeah,
question, not
yeah,
a
exactly.
ring question, but is phi inverse of A intersect B the same as phi inverse of A intersect phi inverse of B?
Yeah, yeah. I remember that from
I think
triple.
that's true, but I
Yeah.
don't think it's true the other way around.
Like
I don't think that phi of A intersect B is the same as phi of A intersect phi of B. I think there's a containment. It's not equal.
E of A
So I
intersection
think I
B.
have to be a little bit more careful about saying, oh, these correspond to these, so their intersections correspond to their intersections. So I think I've got to write some stuff down. I think it's the right idea.
Mm-hmm.
I think that the lattice isomorphism theorem is the way to go. But I think I'd need to be more cautious about those intersections.
Yeah.
The intersections that show up in the definition of irreducible.
Right. So if we have an element both in A and B, then that doesn't mean the image of that element is also going to be in both A and both in the images of A and B. Yeah, makes sense. It's a straightforward logic, but yeah, sometimes you forget. Hmm. Okay. Yeah. Yeah, probably the way that I was thinking was pretty much wrong because I'm not sure what's wrong with it, but something looks like it is wrong otherwise. I mean, mm, mm, you have the ideals that contain I, and you like they are one element subtracted from the rings, and then like you do that for all the elements of the ring. Then when you take the intersection, you're just going to be left with the only things that they contain, that is the I. Hmm. But okay, anyways, we did a lot of progress on this. It was pretty great. Um, let's quickly go through the other problems that we have for today. That we didn't go through. So let's start with problem one, which asks you about the center of a ring. Alright, so the center of a ring is just the set of all the elements that commute with all other elements of the ring. So you have to prove that this center is a subring, and when you have a division ring, the center is going to be a field. That's because you have the commutatively working there. But so this is from Balto's solution about proving that um, it is the center is subring, right? So mhm. So yeah, you have to check that it is not empty. You know, the zero is going to be always there, and then you have to check that you know subtraction is working there. So if you take two elements from the center, their subtraction also is in the center, and that's pretty straightforward to see. And you have to show that the multiplication works there. Yeah, precisely. Maximal implies prime. Prime implies irreducible weight. Does prime imply irreducible in every ring or just in Z? Maximal implies prime, that's for sure. Okay, let me go back to that thing again. Where was that? So prime implies irreducible, that's correct, yeah. But for irreducible to imply prime, you need a UFT. Okay. The homomorphic image of an irreducible ideal is irreducible, and that will be enough to prove part B. Irreducible ideal is irreducible. Looks like it. But yeah, so that was problem 1. Problem 2 is pretty much straightforward. You have to prove that if R is an integral domain, then the elements are inverses themselves. And the proof is pretty straightforward. If you have x square is equal to the identity, so the x square minus the identity is going to give you 0. Okay, yeah, that makes sense. Okay, I think that's what others have also done. Yeah. We know there's a maximal ideal that contains A. How do you know there's a maximal ideal that does not contain A? Wait, I'm not sure. um,
Sorry, back chat between me and Brian.
Okay.
We don't have to keep talking about the last problem.
No, the thing is, I mean, did you realize something that does not work or something?
Oh no, I think Brian was in chat was suggesting a
Okay.
different proof of the last problem.
Mhm.
I was just following along with that. Sorry to interrupt.
Yeah, so that was problem 2, just pretty straightforward. Problem 3 is about, having two rings and then the direct product, and you have to prove that the direct product is commutative if both the rings are commutative. So, yeah. The addition multiplication is pointwise. Pointwise is defined. You have to just prove that multiplication has the associativity and distributivity laws, and I mean you already have the additive abelian group because of the direct product. So you have to show that when you multiply, three different elements, you can have the associativity, and it follows from the fact that it's pointwise. So yeah. And if you have commutative rings, then the multiplication is going to be the same, right? R1, R2, comma S1, S2 is going to be equal to R2, R1, comma S2, S1. Makes sense. Then about problem 4, you have this is from Luffy. An element is going to be nilpotent if you have some n such that a to the n gives you 0. So you have to prove that if a and b are nilpotent in R, then and they're commutative, then a plus b is also nilpotent. Yeah, so yeah, he takes two elements that are nilpotent in the ring. Then there exists like L k is such that a to the L is equal to b to the k, that is equal to 0 for some Lk. Then you know wait. You expand the binomial for a plus b to the n, and you're going to get something like this. And here it's 0 because b to the n minus 1 is 0 for all I. N minus I is 0 for all I. Wait. Yeah, AI is 0 in the second term, and here BA to the n minus I is 0. Okay, so it will be like n minus n over 2, repeatedly, so n minus n over 2 is just n over 2, and you're taking n to be 2 twice of the maximum of L and K. Okay. So you're going to have the maximum element here for n minus I, and then for I you're going to have it here, so the whole thing becomes 0, making a plus b nilpotent. Yeah, and you can write this only if AB is equal to BA, so they're commutative under multiplication. Yeah, cheer does the same, but kind of. Yeah, a plus b to the m plus n minus 1 is going to be you have to add all these and here if I is like less than m, then b to the m plus n minus 1 minus I. So this is just like Balto took this as like n minus I. But yeah. So here it's going to be 0 if I is less than m. B is going to be 0 if I is greater than or equal to m. A to the I is going to be 0. So your whole thing comes to be 0. Okay. Problem 5. If you have two rings, and you have a function that preserves both operations, so this is not a ring homomorphism, but something that will be. I mean, yeah, if you have other conditions, it's going to be a ring homomorphism. So it preserves both operations. So you have to prove that if it is surjective, then phi of the identity under R is equal to the identity under S, and all you have to show is that as it's surjective, so for every S that you take in the codomain, you're going to have something in R. So when you like when you map the identity from R, oh, I think you missed out something here. This wait.
Your voice is getting a little choppy, Divya.
Is it? Is my screen visible or is it also lagging?
No, the screen's fine. It's just your voice seems to be dropping out. At least on my connection, it sounds like you're dropping out.
Okay, I'll rejoin. Is this better? I guess not.
Again?
Is this better?
Yeah, it sounds good now.
Okay, yeah, nice. Okay, yeah, let me stream again. I think something was wrong. Okay, that's fine. Where were we? Problem 5. Yeah, the identities. Ah, you've written a lot. Okay. Yeah, yeah, right. So, yeah, this is right. So this is, I think you missed, I think, the step here. Phi of one in the ring R. So the identity in R is mapped to. You can write it as the image of the identity times the image of the identity. Yeah. No, you can write that like the image of the identity times the identity under S, right? I mean, stating this doesn't do anything. Or does it? Oh, no, it does. Because you can write this as phi of 1r is equal to phi of 1r times phi of 1r, and you can write both of them as like 1s phi of 1r times phi of 1r, and then it cancels down to get phi of 1r is equal to s. I mean, the logic is, of course, making sense, but it's the way he wrote. Okay, so now if you have an integral domain, you're going to take an element of the ring.
So that was actually a proof of part 2.
Which one?
Actually, the cancellation law assumed an integral domain.
The cancellation law assumes an integral domain? Wait.
So where he says by the cancellation law,
Yeah.
cancellation laws rule in integral domains. And in part 1, we're not told that we have an integral domain. That's part 2.
Ah, yeah. Okay. Next. Yeah. Yeah, that's the thing. You don't really need that. I mean, you can just take an element, map the multiplication of the element to the identity, and you'll get phi of a times phi of the identity under R, and then wait, if you do not use the cancellation law, how are we going to do this?
I think this
Okay.
one-line proof captures it. The one
Yeah,
on screen that you just had on screen.
yeah, exactly. Makes sense. You can just use surjectivity to um, get this. In the first case, you do not need the cancellation. Yeah, so this is by cheer. And this is yours. Yeah, you can write every b as the phi of some a, and a can be written as a times the identity of r. So you can then write it as phi of identity of r times phi of a, and phi of a is b. Okay. Yeah, you show that phi of 1r is both a right identity, so right and left identity. Yeah, and then you're going to make it. So this is better.
It's the same thing Cheer said, only I took 5 lines to write it instead of 1.
It's better. It's still better to write 5 lines. Not everyone has to be into party. Okay, so that was problem 5. Problem 6, 7, 8. 6 is about an ideal and a subring. We have to prove that the intersection is an ideal of the subring. Yeah, I mean the intersection of subrings is a subring. So I intersection S is a subring. You just have to show that the multiplication works under I intersection S. Then it's going to be an ideal. Yeah, and that's what you did. The next one is showing by example that not every ideal of a subring of a ring R need be of the form I intersection S for sure. So the counterexample is, yeah, if you have like R and Z, mm, yeah, because R is a field, right? You're going to have only the null and the unit ideals. So the only ideals of S of the form I intersection S will be 0 and Z, right? Because hmm, because you do not have any other ideals which you can include, which you can get from R. Right? Okay, I feel like, yeah, the early problems were pretty easy. It was only the 10th that bugged. The 7th one is about the polynomials. So if I is the ideal of all polynomials in Z, X, you're trying to see if the set of polynomials whose first non-zero term has degree at least n. Okay, so yeah, so the first non-zero term, that is a to the n x to the a n x to the n, has degree at least n. Okay. By definition, an element of I to the n will be a finite sum of elements of the form f1 till fn, where each is a polynomial in Zx, with 0 as the constant term. Since each product of this will be a polynomial of the form axn plus terms of increasing degree, a finite sum of such polynomials will again be of this form. Yes. Yes, and then yeah, as this is like, you can take this is an increasing, your powers of each x increases, so you can take n minus 1 common out of all this, and then have another polynomial of degree m plus 1. Yeah, I think like this was pretty much what the example and the uh, endowment was about. I think it talked a lot about these polynomials and how they work. Next, about the nilpotent ideals. So an ideal is nilpotent if n to the n is the zero ideal for some positive n. Prove that this thing is a nilpotent ideal in Z mod e to the mz. Okay, I mean, yeah, so if you consider the ideal generated by NP, which would be in the quotient of PZ mod e to the mz, right? So it's going to be NP. Mm-hmm. Then z mod p to the mz is commutative, yeah. Okay, so if you just raise the powers, we know how powers work with ideals. Yeah, that was one of the um, results using the finite sums. Um, you can have np raised to the power m is equal to n m pm, the ideal generated by them, and that's equal to the zero ideal, which is in, okay, makes sense. That's an important ideal in the ring z mod p to the mz. Okay, that was a neat proof in one line. Um, that was 8. A nine is straightforward. 9 was just something we did in damage, so yeah, there's that. The proof is pretty much straightforward. If you have a non-zero ideal of the field, the thing is, in the field you have every element has an inverse. Yeah. Okay. Hmm. Okay. You have a homomorphism where the kernel of the homomorphism is going to be the field itself, right? So in which case the homomorphism is the trivial homomorphism, or if the kernel is the zero ideal, then it's going to be injected. Hence, it maps field onto its image in R. Okay, yeah. This was we saw this yesterday. Just didn't go through the proof because it was in the P set. Other solutions, anything interesting? Hmm. For important problems. Okay. He takes three ideals of a ring. One is contained in another, so I1 contains I. So he considers the formal sum of two elements from I1 and I2. Right, so x is equal to the summation of AI plus I. Okay, AI plus the ideal and bj plus the ideal. Okay, so you have two indexes that sum all these, um, making x to be an element of I1 mod I times I2 mod I. Yep, and from one of our propositions we can take I out of it and it will still be an element. So this is going to be an element of I1 I2 mod I. Okay, so he showed that. Okay, so this, I mean, did he have to show this? Wasn't it like one of our theorems? Yeah, so then, okay, Then he applies this to the problem that we have.
I wish he were here to say why he thought he needed to do that.
Exactly, I don't see the reason to.
Maybe I was too hasty.
Cheer, kind of is something similar. Okay. Px plus p to the mz is then pz mod p to the mz. Then you raise that to power m. That will be the summation of px to the I plus minus p to the m to the power m minus I. Ah, hmm. Okay, so px to the power m plus p to the mz is equal to p to the m x to the m plus p to the mz, and that is equal to 0. Yeah, because we have the nilpotent elements. Um, hmm. That is equal to 0 plus p to the m z. Okay, I'm not too sure about this now. Okay, yeah. So that was the p set. The big thing about today was Bourbaki's problem. He did that. That's a great achievement. Um, yeah, well done, JP.
I haven't been able to write down a proof of part B yet, so there's still work to be done there, I think.
Part B. Okay, let me.
I really do, for the proof I have in mind, I really do need to have a one-to-one correspondence between irreducible ideals in R and irreducible ideals in the quotient. I mean, irreducible ideals in R that can contain I and irreducible ideals in the quotient. And I'm short one containment.
Okay.
So I'm going to have to keep playing with it. I think I may be close, but I'm out of ideas for the moment.
Okay, yeah. But yeah, at least we did A, so that's good.
Ooh, I'm pretty happy about that. Good session.
Yep. So tomorrow we have some more stuff to go through. We have the whole chapter 8 to go through on UFDs and PIDs. So we'll go through that, and we have the last piece set on ring theory, which will be due next Wednesday. Right, so then we'll be done with ring theory. We'll go back to group theory for 2 weeks before doing modules. So yeah, it's been pretty great. Yeah, see ya guys tomorrow on the lecture.
This has been an intense week, but it looks like things might lighten up a little bit next week. At least we're not covering 3 sections a day, right?
Indeed. Okay. Yeah.
All right. See y'all tomorrow.
Yeah.